Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view from the scientific community regarding the challenges and opportunity associated with exascale computing, but more broadly about high performance computing to study turbulent flow. So this podcast is linked with the UK Turbulence Consortium and the UK initiative called ExCALIBUR, which is a big 5-year project aimed at redesigning the software in the UK so that we are ready for the transition to exascale computing. So today I'm pleased to have a guest from UCL in London. It's Professor Thorsten Stoesser, who is Professor in Civil Engineering Fluids in the Department of Civil, Environmental and Geomatic Engineering at UCL, so University College London. So he has research interest in developing CFD tools and their application to solve environmental fluid mechanics problems. So it's a great pleasure to have him today. So good morning, Thorsten.
Good morning, Sylvain. Thanks for having me on.
No worries. So I'm going to start with my usual question. So for those who don't know you or don't know you very well, can you tell us a little bit more about yourself, where you are from, what you have studied, and of course, how did you end up at UCL?
Yes, I am Thorsten Stoesser. I'm from Germany. As you can hear from my accent, I can't hide it. I did my undergraduate at Karlsruhe Institute of Technology, also the MSc. Back in these days, it was called a diploma engineer, but it's sort of the equivalent of the BSc and MSc. And this is when I first started to use CFD in a third-year project, and then that carried over into a master's thesis and or master's dissertation. And yeah, I've never looked back since. Started to ignite my fire for CFD. And then I did a PhD at Bristol University, where I was fairly free in choosing my own topic. That was quite attractive. So it was definitely around CFD, and it was in 1998. And my supervisor, Paul Bates, at the time said to me, look, we have an interest in large eddy simulations. This is sort of a new technique that's been sort of looked at. How would you feel about doing some LES? And I was really glad to take that challenge and that opportunity, develop my own CFD code or LES code, finite volumes, curvilinear grid. It was painful for months and months. I tried to solve these equations, but succeeded. And then funnily, I came back to Karlsruhe to work with Professor Wolfgang Rodi. And back in these days, early 2000, they were, already one of the world leaders in large eddy simulations. And I was gladly taking this opportunity to learn more, to develop code, to apply code, and always around civil engineering sort of questions. It was, yes, when I started, it was sort of flow around a cylinder, square cylinder actually was part of my PhD thesis. But it quickly developed into flow over rough beds, turbulent structures, coherent structures. And yeah, that was really good. That was really productive, learned a lot, and then went to Georgia Tech because I came towards the end of my postdoc contract, had an opportunity to interview at Georgia Tech, was encouraged by Professor Fotis Sotiropoulos, who's also quite known in this area. And yeah, got the job offered, went to Georgia Tech in 2006, started as an assistant professor, really hard, really tough years, but a lot to learn again. Teaching came on, and then PhD student supervision, grant applications, yeah, it all sort of, one thing, one step at a time. And then 2012, I went to Cardiff University, had a full professorship there because my family and I, we wanted to be closer to Germany. Cardiff was a great opportunity. And then in 2018, I was invited to interview at UCL. Apparently did not so bad, and got the job offered, and yeah, and enjoy it a lot. UCL is fantastic. London is great. Yeah, fab decision. Definitely no regrets.
Great. Thank you very much. And so I have another question. So you've been working in Germany, in the US, in Wales, now in London. So I'd like to know what's the best thing about your current position and about working at UCL, and maybe how does it compare, with the US or with Germany?
Yeah, I mean, Germany, I can't say so much because I was a postdoc. I was really well under the mentorship of Wolfgang Rodi. I just had a job to do. I did my simulations, published some papers. The systems are really different. Germany, you have the big professor at the top, and then there's basically nobody else underneath them, and then the postdocs and the PhD students. In the US, is very competitive, fantastic opportunities. It definitely helps you grow if you make it, of course. I think the tenure system in the US was a big challenge for me, especially being at Georgia Tech, one of the top universities. And that really, I would say, helped me develop into the academic that I'm now. Cardiff in Wales is a little bit different to let's say Georgia Tech. It was a big step. One would say, why do you go from Georgia Tech to Cardiff? That doesn't make any sense. But for me, I mean, I was a full professor at Cardiff. I had a bit more freedom. And obviously, I had to establish myself in the UK, which went quite smoothly. Worked with Professor Falconer there. That helped me a lot. And then going to UCL, of course, UCL is a top institution. Is one of the top universities in the world. London is fantastic. Lots of opportunities, great students. And you have the freedom to think outside the box. I think that was the big draw for me, to be honest, is to say, look, yes, you have to do your teaching, but be free, think what you want to do, what you want to accomplish. How can you help society with what you do? So yeah, I think that was a massive step as well. So. And I promised my wife that this is going to be the last position. So
good. Great, thank you. So can you tell us a little bit more about the projects, very briefly, the projects you are working on at the moment?
Yeah, at the moment we have 3 EPSRC projects. 2 are with Sheffield University. One is on turbulent flows in pipes. These are all free surface or let's say open channel projects where the water surface deformation is key. One is in pipes. We want to learn how turbulence affects or how we can find leakage in pipes, in underground pipes, by looking at the turbulence and how the turbulence can be picked up near the wall. So near wall turbulence, when you have a crack in the pipe, the signature of the turbulence will change, and that can be picked up by some sensors or some measuring devices. And so you don't have to really crawl into these pipes, into these mostly sewage pipes, to find the cracks. Hopefully this can be found or detected remotely. That's the pipe project with Sheffield. And then we work on a project with Sheffield on free surface deformations, where we try and use drones that fly over over a flooded river, let's say. And then by the way the free surface deforms, or the water surface deforms, one could calculate back what the flow rates are, what the velocities are. And so this could help like the Environment Agency to monitor rivers during flooding. When you have these extreme events, climate change, you know, we've seen this. There was a big flood in Germany, you know, nobody seemed to have realized how massive that flood was until it hit the villages, and lots of houses and property got destroyed. So, and we see this again and again. So monitoring, warning the people in the villages, early warning. I think that's where this is where this project goes, and this is how this project can contribute. Then we have a project with Aberdeen, Southampton, and Glasgow. This has just started. This is on secondary currents in channels, pipes, ducts, and boundary layers. So, you know, recently there has been some new findings on very large scale motion, in particular these secondary currents, and how these secondary currents can influence this very large scale motion or suppress it. And this is what we are looking at, is a suppression mechanism, because when you suppress the very large scale turbulence, you may be able to, you know, reduce drag. Or, I mean, there's quite fundamental work. We have just started, so we don't really know yet where it's going. We have 3.5 years, so quite exciting. And then during the COVID pandemic, we did some work for Transport for London. We did some large eddy simulations of aerosol transport in a bus. We all read in the news about the bus drivers who some of which unfortunately passed due to COVID. And so Transport for London approached us and said, you know, how can it be that our bus drivers get sick and get infected? You know, what can we do? And, you know, there was a lot of uncertainty last year around the subject, and we did some large eddy simulations, and this is where we could have used larger computers. We ran some of our simulations on the Met Office's Cray, because that was the largest computer that was available. Then there was some hacks, so we it was a challenge. And then finally we are working on the Airbots project with Loughborough and other partners, where we look at venues and like the Wembley Stadium or operas or the Royal, what is it called? The Royal Albert Hall, I think is one of them. Yeah, so how do the aerosols get transported, and where do they go, and how safe is it to have all the people back, and you know, so on and so forth. So hopefully these projects will also give us some new insights and some ways to move forward and out of this situation at the moment.
Great, thank you very much. Let's talk a bit more about the software. And I know you are using Hydro 3D for some of your research. So would you be able to tell us a little bit more about this this flow solver?
Yes, Hydro 3D is the solver that I actually started to work on at Bristol during my PhD. It got a big change while I was at Georgia Tech. As I said, we started with collocated grids, curvilinear, and sort of more like a RANS type of solver at the beginning, because that was thought to be the best way forward, or at least I thought. and then realized that maybe this staggered grid is a bit more advantageous, and just sticking with Cartesian grids. So we made a big change while I was at Georgia Tech, to go from curvilinear collocated to staggered Cartesian. And then some of the developments that are pretty crucial, I thought, was to get the water surface, free surface for open channel flows, quite important. Also for waves, we do some work on waves now using the same technology, which is the level set method. We've been quite happy with it. got us some really good results. And then because of the complexity of the geometry, we decided to stay with Cartesian grids just for efficiency, and then you use the immersed boundary method, which has also proven to be quite a fantastic way of including complex geometries and also moving boundaries. Fantastic way of resolving moving boundaries in the fluid.
And what's the polarization strategies based on MPI or hybrid OpenMP MPI?
It started out as a pure MPI, where you have your domain decomposition into blocks and then just transfer information at the boundaries, and then we added an OpenMP to it, simply because of immersed boundaries. We also did a bit of work on Lagrangian particle tracking, and again, this is where you have a lot of points and a lot of overhead in one block, and then you need something to deal with it, because otherwise that block is very slow and is way behind all the other blocks, and you lose a lot of efficiency. And so we added the OpenMP strategy or the OpenMP to it, so it's a hybrid. So when we have immersed boundaries that are clustered in one block, then all the immersed boundary routines are being solved via OpenMP, and we just add additional cores locally. We try to do a bit with GPU as well. This, I think, is very exciting, but haven't had success yet, simply because I had a PhD student who was supposed to do it, and he dropped out after 6 months and he didn't like it. So yeah, so what can you do? So maybe that's something on the horizon. Marry the OpenMP MPI with CUDA and GPU. So maybe.
Good. Thanks. So you mentioned, I mean, I know you have lots of experience with free surface flows, and you mentioned the level set methods. Would you say that if one wants to simulate free surface flow, the level set method is the best method, or you think we should also be looking at other approach? What's your view?
I'd never say something like that. I'd never say this is the best method, or you should do this or that. I think for us and for our solver, level set works really well. I know my colleague at Cardiff, Chuak C, he does volume of fluid, and I've seen a lot of work with volume of fluid, and I think that's also a very powerful technique. Yeah, I think there's definitely various versions of it. I wouldn't say one is better than the other. I would just say we do validate our simulations. I think that's critical, especially when you do LES. And these what we call supergrid models: water surface, free surface, deformation, immersed boundaries. These are not 100% accurate. It's not a DNS. You need some algorithms and some techniques that influence, the simulation or the accuracy of the simulation. So validation, I think, is key. Our method works for the various flows that we've done. And yeah, I'd like to try volume of fluid, but nobody really pays you for developing work, right? So if we had an opportunity to do volume of fluid and try it against a level set, that'll be nice, but we don't really have the time.
Sure. As a follow-up question, I've seen a recent work on the computation of the curvilinear water surface deformation of the flow through a bridge contraction, still in a LES context, of course. So can you tell us a little bit more about your finding from this work?
Yeah, I think that was the paper with Sibel Kara, one of my PhD students at Georgia Tech. She was actually the one who developed the level set method for us, or for this code, for Hydro 3D. And one of her papers was on comparing the level set method, or the deformation of the water surface against rigid lid. You know, when you have a deformed water surface and when you do simulate the same case, but with rigid lid, and we saw big differences. It made a big difference. You would think, yeah, there's a bit of water surface deformation, and it wasn't all that much, to be honest. But the turbulent structure changed, and I think that was a big eye opener. I think that was, and I think we've got quite a few sites on this paper already, yeah, and others have followed. I mean, there's the Fotis Soteropoulos group. They've done level set method. I think they've even done it before us. But to show and to see that the free surface deformation, albeit quite small, makes a difference in what's happening underneath, that was quite surprising, but also nice to see that it you know, it has value to do it. It's an overhead. It's an additional computational cost. The level set method is not cheap in terms of computational cost, but if you want to be accurate and you want to reproduce reality, that's what it takes. Great,
thank you. And another follow-up questions. I mean, you talked a lot about immersive boundary method, and you have been working with immersive boundary method to look at blade vortex interactions for wind turbines or for underwater turbines. So can you tell us a little bit more about your work on immersive boundary method in a LES context?
Yeah, absolutely. Yes, I think that's one of the big, let's say, bonuses or positives of the immersed boundary method, that you can simulate fairly accurately. I wouldn't say it's the most accurate method, but fairly accurately moving boundaries in a fluid, in a background fluid. Let's say the background fluid is Eulerian, and you have it resolved on a fairly fine grid. But what do you do when you have like a rotor spinning inside that fluid, inside that background fluid? And of course, you can't resolve that by the grid because the boundary is moving. And so we use this Lagrangian, it's kind of a Lagrangian method, if you like. So it's a bunch of points that's traveling through the fluid, and then of course you give that bunch of points a shape, which is the blade shape of a wind turbine or a water turbine, and then you just need the computational power to resolve it fine enough. Because in these applications, the boundary layer separation is key. We've done some work on this on a moving blade or pitching blade. We've done some work on that, and my PhD student Pablo Uro, who is now at Manchester, did that work, and it took us a while to figure out how to then go from to learn or to calculate all the forces that are acting, and to transfer that into a torque and thrust on the blades, and then from the lift and drag, and then calculate the performance of these blades, so or of these wind or water turbines. So, and we published a paper in 2017 on this vertical axis turbine, and we found some quite interesting flow features, turbulent structures, how they come off the blade and how they interact with the background flow, and how other blades or other rotor blades then interact with these vortices that are shed previously. So all in all, a lot of development, a lot of testing, a lot of validation. But that's definitely a paper and some work that we can be proud of.
Great. One final question about the blades and turbines. I've seen a recent publication about vertical axis turbines with deflectors. So can you tell us a little bit more about that?
Yeah, absolutely. We this is a partnership or a collaboration with a university in China, Dalian University. I was invited to be on a workshop at Dalian. When was that? That was 2018, I think, when we was just the year before Corona. Was it 19 or 18? I can't remember now. I think it was 19. Anyway, we had done quite a lot of work on vertical axis water turbines. And in Dalian, my collaborator, he did quite a bit of work on vertical axis wind turbines. And so it was quite natural that we work together on this, especially because we had looked at twin turbines, you know, where you have two turbines, two vertical axis turbines, and they counter rotate or contra rotate, if you like. And so the challenge here is to obviously place these and to so that they, you know, gain off each other, gain performance. And so my collaborator at Dalian had done some wind tunnel tests, and he said, you know, when we put a deflector in the middle, we would even get a better performance because it accelerates locally the flow or the wind, the air, and then the blades travel into this accelerated air, and obviously gain a bit of performance. And so this is how this project came about. He had a PhD student, was it a PhD student? I think his student worked on did the simulations. And so it was quite natural that we worked together on this and got some decent results. Great. Definitely interesting results for sure. And, you know, always food for thought. And to move forward and to do the next thing. So
great, thank you. I have a couple more questions about HPC. You mentioned in the introduction that when you were working on the aerosol simulation, you were struggling to find some computational resources, and you went to the Met Office supercomputers. But basically, I'd like to know what you think if tomorrow you have access to an exascale supercomputer or very large scale supercomputers. What do you think you will be able to do that at the moment you cannot really do because you don't have enough compute resources?
Yeah, I mean, of course, the exascale is a dream, right? And it continues. It continues to get faster and to get bigger. These HPCs. Believe it or not, when I started at Georgia Tech, there was all the talk about terascale, you know, and I said, oh, if we had a terascale computer, we could do this and this and this and that, and just a few years later, yeah, like 8 years later, we're talking exa, you know, factor 1,000. It's just enormous. It's fantastic. So yeah, I mentioned the bus simulation, where we really came to our limits. You know, we had these simulations on the Met Office's Cray. We looked at the double-decker bus. These double-decker bus, you know, were the biggest concern for TfL. And so we simulated the lower deck, the lower level of the double-decker bus, because we couldn't afford to simulate the whole thing. And so when I presented this work at a workshop, like when was that, last year, sometime in the summer, you know, we were criticized, you know, what about the boundary conditions? You know, the bus travels at a certain speed, and how do you know how much air is coming into the bus when you open the doors? You know, how much air is coming into the bus when you open the doors, when you close the doors, because there was the question of door opening. You know, the TfL decided to keep the front door closed and only open the middle doors, and we sort of had you know, to make a good and estimated guess of how much air is coming in when the bus stands at the stop for 90 seconds. And we got criticized and said, hang on a minute, we're doing here most expensive large eddy simulations, details around the driver's cabin, how the aerosols enter the driver's cabin, and you criticize us for the boundary conditions on the door. And I said, if we had the power and the computational resources to do the boundary layer around the bus, I would have done it, but we were limited. We were pushing the Met Office's supercomputer to the absolute limit to get quickly results, because these results were important for TfL, for the drivers, for passengers. I mean, this was not a research project as such. It was like really applied. And it was important and imminent. They needed answers. Every meeting we had with them is that, do you have new results? Do you have new results? When do we get new results? When can we make a decision? So an exascale HPC would have been fantastic. So yes, long-winded answer, but bottom line, yes, of course, we'd love it. We'd love to have one.
Great, thank you. I have one final question. It's more like a philosophical question. It's about where do you see HPC heading in the future? I mean, we are talking about exascale computing. You mentioned possibly working towards GPUs, software development, because I think it will be unavoidable. But if we look on the long term, like 15, 20, 30 years, where do you think we will be running our simulations on that time scale?
Yeah. I think of course, the computational resources are going to grow. There's absolutely no doubt about that. I mean, I mentioned the terascale computing just 8 years ago, and now we're talking exascale. So one of the things that I hope is going to be put more resources behind is just the entire framework around it. Crunching numbers, floating point operations per second, with raw power is easy. Let's say is easy. But what is important is the infrastructure around it. And my students are struggling with visualization actually, and data management. And downloading the data on a secure on a secure line takes days. Processing these, again, I'm talking about these large bus simulations. Processing some of these results takes days. Analyzing takes days, weeks. It's just the infrastructure around it needs to grow with it. It doesn't. In our case, it doesn't grow at the same speed as the raw computing power grows. I think this is where I hope we'll see some more breakthroughs. And of course, our algorithms in our particular niche, let's say the civil engineering fluids, we talked about water surface, free surface, and we talked about boundary, rough boundaries or boundary treatment. I'm also hoping that there will be new developments, new algorithms to solve new and complex problems. Flow through vegetation is one thing that we're looking at, I have been looking at over my career, is where you say, okay, nature is complex. If you flow around a circular cylinder, it's easy now. But what about a plant, a real plant that deforms, that has leaves, has little branches? How do you do that? How do you discretize it even? That's a key challenge. Sediment transport is another key challenge. Again, the physics is behind the raw computational power. Understanding how sediments get lifted off the bed around a bridge pier. We kind of have a rough understanding of what's going on. Turbulence plays a big role, we know it. But how do you describe it? How do you put it into equations? There's no equation for it. Well, there is equation for it, but how accurate is it? There's empiricism in it. And so, again, if we could do everything DNS, how we would do it. but sometimes we don't even have the equations for it. So that's
Good.
where I hope we catch up, and that's where I hope the community catches up with the incredible development by the HPC companies, manufacturers. So maybe we can do a tiny little part of this.
Great. Thank you very much, Thorsten. It was very nice chatting to you, and we would like to wish you all the best for your future endeavors and for your EPSRC projects and collaboration and everything. So thank you one more time for your time and your inputs.
My absolute pleasure, Sylvain, and thanks for having me on.
Great. Thank you, everyone, for listening to this podcast. As usual, you can find all the links on the UK Turbulence Consortium website. So just Google UK Turbulence, you will find us very easily. And you will also find all the links on Twitter. Once again, it's UK Turbulence as the UK Turbulence Consortium. So thank you very much for listening, and hope to see you very soon in the new episode of the podcast.